Hi, welcome to the second video in our series, Programming Autonomous Cars on Unity. In our previous video, we looked at the Perceptron and its simple mechanics. Today, we will follow that same train of thought and explore the multi-layered Perceptron, which we will use to help our cars on Unity learn. Multi-layered perceptrons are exactly what you think they are. Multiple layers of perceptrons or neurons. A single perceptron and a multi-layered perceptron differ greatly in complexity and performance. There's a lot more complexity involved with programming multi-layered perceptrons, which we can also refer to as the MLP. Though with that complexity comes higher performance and output complexity. MLPs can be used to solve nonlinear functions and problems. So let's break it down. Here's an image of a multi-layered perceptron. Now, generally all multi-layer perceptrons follow the same three structural layers: input, hidden, and output layers. So there are three different types of nodes that correspond to the structural layers: input, hidden, and output. Input nodes take in external outputs, and no computations are made in the input layer, and so the only output coming from the input nodes are from the external outputs. It's referred to as the hidden layer because the user is never able to see any of the interactions that occur in the hidden layer, so it's hidden. The activation function that we mentioned in the first video also happens in the hidden layer. Remember, the activation function returns an output and it adjusts these values, altering the values so that they fit within a certain range. The output layers take input from the hidden layer and they perform similar calculations as the nodes in the hidden layer, like the weight summations. Okay, next let's look at the connections between the nodes. In this multi-layered perceptron, all the nodes are fully connected. The term fully connected explains how each input from one layer are connected to every single node in the next layer. Each connection between two nodes has a weight value. In an MLP with multiple hidden layers, you can have up to hundreds of weights that you need to assign to each connection. So in the hidden layer, the node of the hidden layer processes input from the nodes in the input layer. Then it calculates a summation weight, passing this value through an activation function, which returns an output to pass to the next layer. Now we need an effective way to pass these inputs back and forth. The most traditional way of doing this is through a matrix, which can be seen as a series of vectors or an array of arrays. Using matrices, we can multiply the inputs by the weights in the matrix to determine the output of a hidden layer. Let's show the implementation of the matrix with a simple MLP. 3 output nodes, 3 hidden layers, and 3 output layers. So each row in the matrix is a node of a hidden layer. Each row contains the connection weight values passing into the node. So you have as many columns as you have nodes. Using some matrix math, you can quickly calculate the output of each hidden node. So take a look at how we can arrange the matrix given this neural network. So the weights entering the top node are stored in the first row. The weights joining the next node are stored in the row below. This is how we can organize the weights of our nodes. So to find the summation of the weights of each hidden node, we can use matrix multiplication. There are 2 different matrices, one for the inputs and one for the weights of the node. You want to multiply the matrices together to get the weight outputs for each node. So let's try and experiment with some matrix multiplication. So in our case, we will not be using very complex matrix operations. We take in a 1 times n inputs matrix and multiply it with a matrix full of weights with a row of x nodes and n weights. The important thing to note is matrix multiplication is not associative. Matrix A times matrix B is not necessarily equivalent to matrix B times matrix A. We can use a concept called the dot product to find the product matrix, where you multiply matching numbers. To get an idea of what I mean, let's try this question. So we have a 3x2 weight matrix and a 2x1 input matrix. To start, we can use the dot product by multiplying the matching numbers for the first row of the first matrix by the first column of the second matrix. So you start with values 3 times 1 and 4 times 2. Then you sum up these values, and you can express this notation as 3, 4 times brackets 1, 2. And the value that you just calculated is the the first element in the first row and the first column of the product matrix. Now, since the input matrix is only one column wide, you can move to the next row in the weight matrix. Multiply the matching elements with the first column again and the second row in the weight matrix, and you can sum them again to find the value of the element in the second row, first column in the product matrix. So you end up with 5 times 1 plus 6 times 2. So I hope you have started to notice a pattern. The element in the product matrix is placed in a position corresponding to the row or column of the elements that you use to multiply each other. So to apply the dot product, you look at the rows in the first matrix and columns in the second matrix. Let's finish this calculation by finding the dot product of the third row of the weight matrix and the first column of the input matrix. And that's how you do matrix multiplication. And so what is the purpose of this? If you take a closer look, you will realize the multiplication of the two matrices yields a matrix of the summed weights of each hidden node. And so the elements produced in the product matrix correspond to the different hidden nodes. The dot product sums up the product of the weight and multiplication for every input. Therefore, we can save a lot of code using matrices and matrix multiplication. An important advantage of using matrix operation is that it's really efficient for GPU performance. GPUs can quickly do matrix multiplication because of something called parallel computing, in which tasks are broken down and solved simultaneously. We don't need to write any functions to do any matrix multiplication, luckily, since there is a linear algebra library that allows us to do matrix multiplication. So that was a general overview of a multi-layered perceptron. Next video, we will take a look at how to implement the content from this video and the previous video, both the multi-layered perceptron and the genetic algorithm. Stay tuned for the next video and subscribe if you enjoyed.